Assalamu alaikum. This is lecture 12 on digital control system. We are discussing chapter 3, Z-plane analysis of discrete time control system. Today we're going to start article 3.6, that is realization of digital controllers and digital filters. Before that, I forgot to mention you that you should go through example 3.7. This is related to one example that is dealing with digital PID controller and part of it is to go for MATLAB simulation. Okay, so it's optional whether you go about the MATLAB simulation or not, but the rest of it you may take as an example to how to deal with systems with digital PID controller. Also, there is a comment after that example, and that is fruitful in some practical application, I believe. So you better have a look at that one as well. And the last part of that last article is obtaining the response between the consecutive sampling instant. So we know what is happening in current sample and in the next sample and in the next sample and in the next sample, but we don't know what is happening in between. So in between, how they will be connected. So if you want to figure out the in between values, in that case, you have to deal with you have to have some mechanism to figure out those values. So there's three ways to deal with it, and in this book is not been in detail given. The detailed discussion is not given, so I will also not cover that one in detail. Rather, just mentioning the names. You either use the Laplace transform method, and secondly, modified Z transform method. And finally, state space method. Okay, so these are the three methods. A brief of the first one, that is Laplace transform method, is actually been discussed, but eventually, and you can have a look at the other methods in your appendix B if you're interested, but that is not part of our syllabus. So you're advised to look at that one if you want. Now, today's article, that is realization. What is mean by the realization of digital controller or filter? The first of all, what is digital controller and the filter? Basically, the, the filter is something that is you give a variety of frequencies of signal included in a signal. You have different frequencies, and whatever you need according to your adjustment, you just block those. So in that sense, you have a digital filter. You are having a signal and signal of lot of frequencies, say range of frequency omega 1 to omega n. And now with desired band within that one, say omega x to omega y, you want to allow, rest of them you want to block. So this is what is the function of the digital filter. In some sense, the digital controller is also a subset of your digital filter. So in a digital controller, we also do a similar thing. We allow some kind of signal, and based on that, we actually shape the output of the signal. So we can say that digital controller is basically a subset of digital filters. So common name, more common name is digital filter, and the other a particular combine a particular subset of that one can be considered as a digital uh, controller. So now, what is meant by realization? So realization of a pulse transfer function means determining the physical layout for the appropriate combination of arithmetic and storage operations. So basically, whatever the pulse transfer function we have, how can we represent that thing using some combination either in hardware or software? So this is what is meant by realization. So what is, first of all, realization? Realization. So there is two kind. One is software. One is hardware. And software realization means writing computer program. So computer program for dedicated computer or processor. So microcontroller or microprocessor maybe. In the hardware, actually building a special purpose processor. Okay, so you have to build the processor, build the special function or purpose processor with the combination of using your digital adder, multiplier, and delay elements. Okay, so the software one is relatively easier. So you just write the program, and based on the system, you can actually change it as well. But if you build a special purpose processor, in that case, it will be difficult to modify. So nowadays, we shift more towards the software implementation. So whatever, whether you're going for software or hardware, okay, so we can go for any one of them, but we have to have that realization or block diagram realization. And once you have the block diagram realization, the rest of the implementation is just becoming a procedure. So before going further, we can actually go for a division. What is the distinction between digital controller and digital filter? As we said, one is subset of another one. So digital controller is a subset of digital filter, but digital controller is specific on that note that it is actually real time. So the process has to be dealt with in real time, whereas the process can tolerate delay in case of digital filter, which has been used in communication. So digital filter. So for more better accuracy or more accuracy, we can actually tolerate the delay in filters. Okay, so this is the only difference. Now, block diagram realization of the digital filter using, we interchangeably you can call the controller as a filter as well. So in this particular topic, whatever we are discussing is actually we are realizing the digital filter, and it is actually realized using delay elements, adders, and multipliers. Okay, so once we realize that, and then based on that, we can actually go for hardware software design. Okay, so what is meant by how can we represent delay? So in the block diagram representation, basically a pulse transfer function of Z inverse. So a pulse transfer function of Z inverse, how actually that is represented. And we know that in time domain or in frequency domain or S domain, it is actually e to the minus TS. Okay, so which is actually nothing but the delay, pure delay in S plane. So in block, where we can replace is Z inverse can be given in this way. If you have xk, which is a sequence, or xz, then xk will be xk minus 1 divided by 1 unit, and your xz will be z inverse xz. Okay. So this is how we represent Z inverse in the using a delay in of your pulse transfer function. Now, if we have a generalized equation, generalized form of uh, pulse transfer function, that is Gz equal to Yz output by input with B0 plus B1 Z inverse plus b2 z to the power minus 2 goes on up to, say, m number of zeros we have. So bm z to the power minus m divided by 1 plus a1 z to the power minus 1 plus a2 z to the power minus 2, that goes up to a to the power an z to the power minus n. So we are assuming that our poles, that is n, is greater or equal to the 0. Okay, so and what are the AI and the BI? They are actually the real coefficients of the equation, pulse transfer function. Now, this is a general form. So can we have something similar in case of the position form PID controller that we have derived in the last class? So say that the PID controller position form that we had derived is GDZ equal to KP plus KI 1 minus Z inverse plus KD into 1 minus Z inverse. Okay, so now if we slightly rearrange this one, multiply 1 minus Z inverse, then KP into 1 minus Z inverse plus KI plus KD 1 minus Z inverse square. So if we rearrange the thing a bit further, I think it's better to go into the next slide. Okay, so if we rearrange the thing a bit more, then GDZ will be KP plus KI plus KD minus KP plus 2 KD Z inverse plus KD Z to the power minus 2. Okay, and divided by 1 minus Z inverse. Now, we can compare this one with the standard form that we have, and we can write in this way, B0 plus B1 Z inverse plus B2 Z to the power minus 2. And the denominator, we have 1 plus A1 Z inverse plus A2 Z to the power minus 2. Okay, so now we compare this two equations. So what you can get is B0 is basically KP plus KI plus KD. B1 equal to minus KP plus 2 KD, and B2 is equal to KD. Whereas your A1 is minus 1 and A2 is 0. So these are the coefficients of the position from PID controller that we have derived in the last class. Now, let us look at the programming. There is how can we actually how can we have our block diagram representation of the general equation. So there is two methods for that one. One method is known as direct programming. And the other one is called standard programming. Okay, so in the direct programming, how many delay elements you have in the numerator, you have m, and in the denominator you have n. So that many number of mm, delay element you have to use. So we don't share the delay elements. But in case of the standard one, so minimum number you have to use, and the minimum number is the highest one in general. So n number of delay elements will be used. So this is the difference. Now let us have a look at them one by one. So in the direct one, whatever the transfer function we have, that is gz is y z by xz, the form that we have just written. So we just have to cross multiply. So what you are going to get is yz plus a1 z inverse yz plus, so it goes on up to an z to the power minus n y inverse. Just cross multiplying. I'm not just writing the equation again and again. So and the other side b0 xz plus b1 z inverse xz plus goes on up to bm z to the power minus m xz. Okay, so finally you can write that what is our output? Output y equal to, we just subtract this thing is taken to the other side, minus a1 z inverse yz plus goes on. You can actually, it has to be subtracted. So minus a2 z to the power minus 2 yz and minus goes on up to an z to the power minus n yz plus rest of the x1, so b0 xz plus b1 z inverse xz and goes on up to bm z inverse xz. Okay, now how to implement that? So basically what we can see here is that the first x will be first multiplied with this. So one delay element is coming here. So this is, say, your xz. This is the first delay element. Then this is the second delay element, z inverse. Okay, so it continues up to m number of delay elements. Okay, so mth one will be multiplied with bm. So we can multiply with this one, mth one. This is sorry, my one. This is mth, so m will be multiplied with bm, and then it will be added, going to a summing junction. And the first one, xz, is basically multiplied with b0. So we just multiply that one with b0, then we bring it here and add it. Similarly, the next one will be multiplied with b1. So the next one, it shifted one, will be multiplied with b1. So next one will be multiplied with b2. So all of them are plus. Now the output will be actually your y z, and yz will be further delayed with z1 z to the minus 2. Eventually it will be 1, and then it goes up to nth number of, so z to the minus 1. So this is nth one. Okay, so nth one will be multiplied with an, and also this will be subtracted. These are the negative. So nth one will be multiplied by an. So this one is going directly here with okay. So I think we have to adjust a bit. Okay, so This is your an. And the first one is multiplied with a1. So this is where it will go, and that will be also subtracted. Second one will be a2. Okay, so the rest of them will be in between. So similarly here as well, rest of them will be in between. So this is how m number of delay element in the input side and n number of delay elements in the output side. So m n. So in the direct programming, m plus n number of delay element is used to find out the block diagram of the pulse transfer function, or this is basically the direct programming of the pulse transfer function. Okay, so next one is the standard programming. So in the standard programming, the idea is we share the delay elements and we arrange in such a way that we can minimize the number of the delay elements. So how can you do that? The procedure is very simple. The same function that we are using, y z by xz, so that we actually divide it into in between we introduce h, so y z by hz, then you have hz by xz. Okay, so and the numerator will be coming first, that is b0 plus b1 z inverse plus b1, it should be, so b0 plus b1 z inverse plus b2 z to the power minus 2 and goes on up to bm z to the power minus m. And the numerator will be given in this way, 1 by 1 plus a1 z inverse plus a2 z to the power minus 2 and goes on up to an z to the power minus n. Okay, so this one is simply this one, and this one we are assuming to be this one. So now we can just write the equation for y. So y z equal to y z equal to h z into your b0 plus b1 z inverse plus b2 z to the power minus 2 and goes on into bm z to the power minus m. Okay, so now if you multiply this to then b0 hz plus b1 z inverse hz plus b2 z inverse hz goes on up to bm z to the power minus m hz. You can easily represent this one. So we have z inverse goes up to z inverse m number of them. So m will be multiplied by bm. So you just multiply with bm, that will be added together. And the first one is hz. First hz is multiplied with b0, so it will be multiplied with b0. Then you add it here. Second one, b1. Third one, b2. This is how you have to add all of these in between. Okay, so this representation is fairly simple. Now the second representation that we have is hz by xz equal to 1 by 1 plus a1 z inverse plus a2 z to the power minus 2 plus goes on up to an z to the power minus n. So we can write it here in this way that actually h z, which is the output, will be equal to, if you just multiply, then it will be xz minus a1 z inverse hz minus a2 z to the power minus 2 hz, and negative thing goes on up to minus an z to the power minus n hz. So now what we have is how to represent this one. So basically, you need to have a summing junction. Sorry about that. Okay, so you need to have a summing junction where your xz will be coming, and then in the other side you will have hz, and now we hz with lots of delay elements, n number of them. Okay, so but in the middle, you also have to keep in mind that we may also have to incorporate the nth one in the middle. So that is why again it will continue, and finally it will end up with n. Okay, so nth one will be multiplied with an, so no doubt about it. So an, and then it is going there. Okay, and it will be subtracted. So you'll be keeping track of that one. This is the rest of them is actually subtracted. So this is your A1. The next one is A2. Okay, so the rest of them will be coming in this way, same way. Now the point is the point that we you may wonder what will happen to this one. So don't worry, this is just an. Am definitely am is smaller than an, so you don't have to bother about them too much. Okay, so now this is the second part. So actually we have to share them, we have to make them one figure. So that is why we have to look at how can we actually combine those two together. Okay, so is there any way we can make it connected? So let me just erase this portion. How can I select and drag? Okay, let's see. Yeah. Okay, so now what we have is basically from the previous one, what you know is that H0, the output YZ, output YZ, we can keep it here. YZ is from the previous one, we know that YZ is the summation of whatever the H will be multiplied with B0, and the delayed version will be multiplied with B1. So this is what is our H0. So H0 will be multiplied with B0. So it will be coming straight here with the plus and of course. Then a delayed one will be multiplied with B1. So this one will be coming here with B1. The next one will be coming with B2. And finally, it will be going up to BM. So it will be coming here with Okay, so we can give bm here because you have m number of zeros, so you just add it here. So eventually that will give us out. So instead of using m plus m number of delay elements in this method, what we are actually doing is we are using the n, which one is higher. So, and we assume that n is higher than m. So that is why we are using n number of delay elements and we are sharing in between the input and the output. And that is how we can have our standard program. So this is the standard programming, programming or block diagram redirection, based on which either we can write the software program or hardware implementation with the processor. So there are, we can also have different kind of standard different block layout structure for standard programming as well. So that will be discussed in the next class, inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.